Hello, my name is Matthew Newland. This is video 2 for homework assignment 4. In this part, we're going to be coding, solving, and plotting the time-dependent concentration of the temperature profiles for the constantly stirred tank reactor, with the given step changes in the coolant temperature. With the given parameters in this problem, or the information down below, in our information presented in our problem here, it's a little bit messy to read, so I transferred all the data that we had from both our first video, our equations, and all of our given values and our initial values that it's given in our problem. So our given parameters for our actual reactor is that our flow rate in is 100 liters per minute. Our temperature coming in through our flow rate is 350 Kelvin. And our density of the material is also going to be 1 to the exponent of 3, or 1 times 10 to the exponent of 3 grams per liter. Our concentration of our material coming in is just 1 mole per liter. Our volume of the tank is going to be 100 liters. Our heat capacity of our material is going to be 0.239 joules per grams Kelvin. Our activation energy is going to be heat of activation of our reaction is going to be 8,750 Kelvin. Our thermal conductivity is going to be 5 times 10 to the 4th joules per minute Kelvin. And our frequency factor is also going to be 7.2 times 10 to the 10th power joules per minute Kelvin. Our initial values are going to be as such. We're going to have our concentration. Our initial concentration is going to be 0.5 moles per Kelvin, and our temperature is also going to be our initial temperature is also going to be 350 Kelvin. Other values that we're going to need is our temperature of the coolant, which will then keep our tank cool, so we don't have a uncontrolled exothermic reaction. Is going to be 305 Kelvin, and our time for our reaction is going to be 10 minutes. So from here, we can then split our screen into 2 parts. From here, we can start to code with all of our given values. And from here, we, as you see already, I have all of our tools we're going to need imported in already, such as NumPy for any numerical plots we're going to use, or numerical devices we're going to use. We're going to also use SciPy integrate with our solve IVP to use an integrand function to create our plots. We also have our subplot maker, which is going to be using our plots. And then we have our simple cosmetic plot details, and it's going to be our dark plot just to make things a little bit easier on the eyes. So first we'll start the code. We're just going to separate this off into 3 parts. So this is going to be our given parameters. Then we're going to have our initial values. And then this is just going to be our miscellaneous values. So we'll start off. We'll do our flow rate in first, so it's going to be 100. And then we'll do our concentration going in, which is going to be 1 mole per liter. And then it's our temperature going in, so it's going to be Tn, which is going to be 350 Kelvin. All right, that looks good. Then our volume of the tank is going to be 100 liters. And then our density is going to be 1 times, or we can make that actually, excuse me, almost messed it up. Our 1 to the exponent of 3, or exponential of 3, which is going to be 1 times 10 to the 3rd. And then we have our heat capacity, which is then going to be 0.239 And then our heat of the reaction is going to be 5 times 10 to the fourth. And then our activation energy is going to be 8,705 Kelvin. Oh, almost missed it. We need periods on the end of these. Oh, maybe not that. And then our frequency factor is going to be 7.2 to the power of 10 to the power of 10, or 10 to the 10th. And last thing we need is our thermal conductivity, which is going to be the same as our heat of reaction. So it's going to be 5 exponential to the fourth, if I can write that. These are our values. And then we'll have our initial values, which will then be our concentration going in, our starting concentration, excuse me, and our starting temperature will then be 350. Excuse me. And then our other values we're then going to use is our temperature of the coolant, which will just have TC as our temperature of the coolant, is then going to be 305 Kelvin. And then, I need to go back up and change that just in case that just won't work on us. And then we will also have our ending time, which would then be 10. And this will just be all of our values that we're going to use throughout these equations and throughout our integrands and our integral functions. So what we're going to do next is then create a function for our integration function or our solve IVP. So we're going to make a function. We're just going to call it, since it's a constantly stirred tank reactor, we're just going to call it that. And we need two call functions we're going to use is t, which is going to be time, and then we need our vector, which is our dependent variable. And since we have two dependents here, we have our concentration and we have our temperature. So we're going to set our concentration and temperature equal to our vector. And before we start writing out our equations, we need to do one thing first. We need to set our reaction rate equation. So we're going to take our values from above, our frequency factor multiplied by a numpy function of an exponential function, minus our activation energy divided by our temperature. And this will be our reaction rate for our problem. And and then we want to write out our functions. So we're just going to call this our rate of change for our concentration. So we'll just call it dCA. And that is going to be equal to what we have here. So it's going to be our flow rate in divided by our volume of the tank multiplied by our concentration going in minus our concentration of the tank or concentration going out, because they both are the same because it's a constantly stirred tank, minus our reaction rate multiplied by our concentration. And that will be our first, and move that out of the way. This will be our rate of change for our concentration. And we'll have our rate of change for the temperature. So we'll call this D capital T, not to get it confused with time. We'll have our density, or we'll have our flow rate in divided by our volume as per usual. And then we'll have our temperature values, our temperature going in minus our temperature of the tank, or our temperature going out. And then we have our heat of the reaction times our reaction rate times our concentration divided by our density. And one thing I should point out, usually we don't use, this is technically supposed to be the Greek letter of rho, but I'm just naming it P because pressure isn't a problem in our tank right now, so I'm just calling our density P because the Greek symbol looks similar to a P, so I'm just calling it that, just in case someone would get confused from that. So then we have our density multiplied by our heat capacity, and that will settle that part of the equation. And then we have our thermal conductivity multiplied by our temperature of the tank minus our temperature of the coolant divided by our our density times our volume times our heat capacity. And then what we want to do is then return both of these functions as an array, because only our solve IVP will then take an array, or a solve IVP function will take an array. So we'll just set the two functions that this, or there are two values that this function is going to return is our rate of change for concentration, our rate of change for temperature. So it'll take both of these. So that's looking good. And from here, we can then make our integration function. So what we want to do is then just name our integration function. So sol will be our solve IVP function. And then our function we're going to plug in is our function from here. So it's going to be our CSTR, or constantly stirred tank reactor. And the next thing we want to know is our T-span, or what we our span of time is that's going to pass within our integral. So it's going to be 0. Our starting value is going to be 0 since we want time to start at 0, and then we're going to go to our T end value, which is going to be 10 minutes. And then we need initial values of both our concentration and our temperature, and we already have those up above, so we'll just input those in real quick. Voila. And then we will have our method, will be our Radu method. And then our dense output will be set equal to true. So this should all be looking good. Oh, one last thing is that we want to, this will give a list of integrations that's going to come with it. So we only want to draw our sol value, which is a value that this function will create. So just had to fix that real quick. And the next thing we want to do is then start to set up our plot. So we're just going to name a variable called tplot, and that is going to be equal to a space of points, our numpy lin space. It's going to start at 0, it's going to go to our ending point, and then it's going to go for 500 points, because we want a good solid line that's going to appear on both of our graphs. And the next thing we want to do is then call our concentration and our temperature functions again, using our solve IVP, our integration function. So it's going to be, so we're going to use our integration function and then put in our tplot, what we have from here, into our integration function. This will then use our tplot values in our integration function, and then this integration function will then use values, or take its values and put it through our function to create a list of values we can use in our plots. And the last thing we want to do is make our plots themselves. So we can then set it, our figure, or fig, is equal to make subplots. Oops, spelled that wrong. But we want to, since we have two things being represented here, we're going to do something a little different with our plots this time. What we want to do is we want two graphs, but we want them independent from each other, so we can see how each graph works independent from each other, or not necessarily independent, but we want to see how each graph reacts to the parameters in our equations that we put up. So we're going to have two separate graphs, one for our concentration and another for our temperature. And this will then be, we will set it up as such. We're going to have rows 1, which basically just means both of our graphs will be in one row, and then we need columns to be 2, which will then just make it side by side to each other. So then we can make our plots themselves. So it's going to be fig, add, scatter. Our x plot, our x axis is going to be our t plot, and then our y plot, our y axis is going to be our concentration to start first. So we set that to our concentration. And the next thing we want to do is then make our method, or not our method, our mode to be lines, so we don't have a bunch of points. And then we want to set our this particular function to our first row and our first column. So it's going to be row 1 and then column 1. We also want to name this graph. Concentration. And this should be good. Just gonna go through it one more time until it looks like I messed something up. I think we're good. Then we're gonna copy and paste this whole thing here, since our functions don't really deviate too much. And then we're gonna change something around. We're gonna change this to our temperature, and then we're gonna change this to column 2. And this should be good. And just like that, ooh, I forgot. This is not our concentration plot, part 2. This is our temperature plot. We'll just call it 10. So we have our concentration and our temperature plot. So as you see, we start with a higher concentration and it goes down, and then it repeats over and over again. It reaches sort of an equilibrium with our temperature, which this temperature plot shows that our temperature flies up very, very quickly and then goes back down as our concentration increases again, and then it will then repeat the process. And the relationship between these two graphs is that they're almost the inverse to each other. As our concentration decreases, our temperature decreases, or increases, excuse me, is because that our concentration our material is being used up. So it means our concentration is decreasing throughout this graph. And then our temperature is rising because of our reaction that's taking place within our reactor itself. And then it reaches this point, and then it reaches sort of an equilibrium where our concentration and our temperature sort of stay constant, and they're not going to go back and they're not going to jump really far up here. And we sort of have this smooth, steady graph that jumps up and down over and over again and stays in sort of this steady motion. And this is our whole reactor plot.